So previously we talked about how the periodic table has been organized and how that organization has changed over time. But the model of the atom has also changed over time. So it started way back in the day, even in ancient Greece, there was this idea that matter was made up of indivisible particles. Different parts of matter come together and form new things. Then, in about 1803, other ideas have been tossed around, but a really solid idea came from Dalton, in that atoms are indivisible particles, but that they also combine in small whole number ratios. These ratios, he didn't know it at the time, would be similar to whenever we have water and it's H2O, so like two atoms bonding with one oxygen atom. And he used these ratios. We moved about 100 years later, and a man named Thomson came up with what is called the plum pudding model. But we don't know what plum pudding is in America. We don't really use plum pudding a lot. Instead, we use something called the chocolate chip cookie. We have a circle that has dough. It's just the normal cookie. In Thompson's model, this is going to be the positive area. So the positive area is like the dough. And then the negative areas are going to be the chocolate chips. So remember, in a chocolate chip cookie, the chocolate chips are just kind of spread around everywhere. And that's going to be Thomson's idea. He found this out using something called cathode ray tubes, which are just filled with gas that we put electricity into. Forms a beam, and then that beam was attracted to positive side of the tube when they had like a magnet held up to one side that was positive or negative. So remember, this is important because we're going to talk a lot about like charges repelling each other and opposite charges attracting. At the time, Thomson, he kind of discovered in a way that the atom was divisible and that there was positive and negative substances inside, the negative being electrons. But he didn't know exactly how big electrons were versus the positive part, and he wasn't sure where the mass in the atom was. So in his idea, the atom was all mass, like a chocolate chip cookie, and the negative and the positive were within that mass. A few years later, one of his students named Rutherford did an experiment that proved that actually the atom is mostly empty space and that there's a very dense nucleus in the middle that is positively charged. And he did this using alpha particles that are positively charged, and he shot those into a piece of gold because he knew gold. He tried to get it as pure as he could. And theoretically, these alpha particles, which were very small, basically two proton atoms being shot at a piece of gold, these should just go straight through and not be deflected and not be attracted to them, because these positive and negative charges should have been distributed evenly throughout the atom. Instead, quite a few of the alpha particles went through, but the ones that didn't bounced back at a fast rate. We call that deflected. And they bounced back because there was a dense positive area. So dense means there's a lot of mass there. And this was the nucleus, which we discovered was positive and where most of the mass was. Rutherford said, well, I guess the electrons are just kind of spinning around the nucleus. They're not in the nucleus. But eventually, if they were just spinning around, they would probably lose their energy and come back into the nucleus since they're opposite charges. We know that doesn't happen. So instead, within about the same time frame, Bohr came along and said that these orbits, if you think about space, how planets orbit the sun, similar here. So if we think about the orbit of the electron around the nucleus, it has a defined energy and a defined location. Bohr said that in order for an electron to move to a different orbit, change its location, it either had to absorb or release a very specific amount of energy called a quanta. And then we found out really, we don't know exactly where the electron is at any given time because they're just moving so quickly and they're so tiny. And so Schrodinger, he came up with a lot of complex equations to determine the location and speed. But we can only really give a probability. So we can give a percent chance of where the electron would be at a given time. Because we can't see it, we can't know exactly where it is. So over time, you'll see that the model of the atom changed quite a bit. Each scientist, slowly trying to learn about the atom, might have disproved part from an earlier scientist model. Thomson disproved Dalton's idea that atoms were indivisible by dividing them. He showed that they could be divided in positive and negative ways. Millikan, we don't have his model up here, but he actually added to this model by determining the charge of an electron. And he did this using an experiment with a lot of oil droplets. It's kind of interesting. Rutherford disproved this plum pudding model by showing that instead of the positive charge being all throughout the atom, it's actually concentrated in the really dense nucleus. And this force right here that we have seen probably since elementary school, where like charges repel each other and opposite charges attract, think about magnets and such, this actually has a name, and it's called the Coulomb force. And the Coulomb force is all about charge, so positive and negative,